Hello, everyone. Welcome to the MATLAB and Simulink Robotics Arena. In today's episode, we're going to talk about simulating quadcopter missions using Gazebo. And to join me today to talk about this topic, I've got Julien Cassette from the MathWorks office in the UK. Hello, Julien, and welcome to the Robotics Arena.
Hi, Connell.
Would you want to go ahead and introduce yourself and tell us about how you worked on this project to build a simulation model for quadcopter missions?
Sure. I work in the UK office as an application support engineer in the engineering development group. I have been working on this project for about 6 months, and this is something we started for the IMAV conference and competition that I attended later on.
Oh, nice. So you've actually had some student competition experience.
Yep.
That's good. It's good to know. All right, moving on. For today's agenda, Julian's going to go over the motivation as to why he started working on this project in the first place, and then he's going to cover a little bit about the system architecture needed to set up these simulation models. Finally, he's going to go through how he designed a mission controller in Simulink and going to show you how it is to set up these mission controllers really easily and take it from there. And then finally, we'll do some key takeaways and resources that will help you guys do better at your competitions. So I'm going to hand it over to Julian to let him take it away from now.
Okay, we started this project, as I said, for the IMAV competition. This is an event that takes place every year and which features a conference where researchers present their work with the micro air vehicles. And it also has two competitions, one indoor competition and one outdoor competition, where students have to program a mission for the drone. We wanted to improve how students could use simulation for these competitions. That's why we started this project, because simulation is a low-cost design validation tool, and it would help them to design a controller for the actual competition.
That's interesting. So simulation actually really helps in these kind of competitions, especially when you have both an indoor and an outdoor setting. It's easy to just quickly set up these simulation environments and then run these simulations without actually having a physical drone in place. So that's an interesting project.
Yeah, exactly. So the system architecture is made of two environments. There is the Simulink environment and the Gazebo environment. In Simulink, we design the mission algorithm, and in Gazebo, we have a model of the plant, which is the quadcopter, and a modeling of the environment, which are all the obstacles in the indoor mission, and the modeling of the sensors.
So Juliet, if I got this right, does this mean that you can actually import your own quadcopter in there and then model different environments based on your needs?
Exactly. The quadcopter model is a CAD model that was imported into Gazebo,
Okay,
and the sensors were also designed in Gazebo and then imported.
interesting.
And so those two environments are connected together using ROS, the Robotic Operating System.
Okay.
So Simulink sends command to ROS to control the drone. So these are velocity commands. And Gazebo sends back information to Simulink and sends some data, for example, the position of the drone, the image of the cameras, and the data from the laser scanner.
So just to let our viewers know, my colleague Sebastian Castro, who also creates videos for the Robotics Arena, so he's recently put up some videos on getting started with ROS and talking to ROS through MATLAB and Simulink, which are probably worth taking a look at.
So we are going to show how we use Simulink to design the mission algorithm and to follow some waypoints, for example.
Okay.
And also we'll be able to visualize the simulation result in Gazebo.
Oh, nice. Okay.
In Simulink, we'll implement several algorithms. There is a path following algorithm that allows the drone to follow waypoints that we provide to it.
Mhm.
Also, we implement an obstacle avoidance algorithm,
Okay.
and also an altitude control algorithm.
Oh, okay.
Then using Simulink, we'll be able to tune, test, and validate these algorithms as you would do in a model-based design workflow.
Okay.
And then you can integrate those algorithms so that you can build a more complex controller for the mission.
Okay. Cool.
So now let's start the demonstration of the software. So on the right side of the screen, there is the Gazebo environment. This is a model of the indoor competition. So you can see that there are several obstacles. There are a couple of windows that the drone has go to.
Okay.
We have takeoff and landing pads, one fixed and one that is moving. And in the red zone, we have a couple of obstacles. We have poles and some vegetation. And in the last zone, there is a QR code that the drone has to scan.
Okay.
So here I have instantiated the drone model.
Mhm.
In Simulink, we are going to run the simulation, and what is going to happen is Simulink is going to send the commands to the drone to set its altitude.
Okay, so if I'm correct, I can actually see a block in Simulink that says altitude controller. So is that subsystem giving your drone commands about its altitude?
The altitude controller is a PID controller that will generate a command to maintain the drone to a particular altitude. So for example, here we have
Okay.
set 1 meter as the altitude reference.
Okay.
And there are also a few other blocks to get data from Gazebo. There is the robot position that gives us the position of the robot, the cameras, the laser scanner.
And these blocks are talking to Gazebo over ROS. Are these using the blocks from the Robotics Systems Toolbox?
Exactly. If you look into this subsystem, you can see that there is the ROS block.
Okay.
And we also have ROS blocks in the output subsystem to send the commands to Gazebo.
So you have the publisher and subscriber combination of blocks.
Yeah. Before we start the simulation, we have to set up MATLAB to use the ROS connection. So let's get the IP of the virtual machine. Let's take this IP and use the ROS init function in MATLAB to establish the connection between MATLAB and the ROS server. So the drone has taken off at 1 meter altitude.
It's just hovering because that's all the command that you're giving it.
Exactly. But we also get the data from ROS. For example, this is the position of the drone.
Okay.
And we also get the data from the laser scanner. Here we can see the wall.
Yeah, that actually looks like that wall with the windows in there. That's
what
cool.
it is. We can use the path following algorithms and the obstacle avoidance algorithm and put them in the simulation model.
Okay, so what you've got here is basically a simulation framework of sorts where you can keep dumping in different types of algorithms and testing it in this world. That's actually very useful to teams because at the end of the day you can actually simulate your competition tasks and then just build your design your controllers for your algorithms specifically. That's
Yes, and it's also much easier to test things in simulation rather than in the real world.
Yeah, no, it definitely is. I've definitely spoken to a lot of teams over the course of the year saying, hey, we've broken stuff because we've been trying to test things. So this is actually cool. It's an easy, and it was pretty easy to get this set up. So that's that's definitely a good thing and definitely a good resource for teams.
Okay, let's stop the simulation now and add the path following algorithm. So I'm copying the path following algorithm subsystem to the test environment. So now let's connect this algorithm to its inputs. So I have just connected the the subsystem to the position of the robot, and now I'm connecting the waypoint.
And these waypoints are actually user supplied. So you as a user can actually put in the waypoints and have the drone drive to that uh, to those
Yes.
points.
Here I
Okay.
entered the location of the QR code.
Okay. Okay.
So now I'm connecting the algorithm to the output. So the V signal is the linear velocity signal, and
Mhm.
it contains the speed at which you want the drone to move forward. W
Okay.
is the angular velocity, so it actually drives
Mm.
the rotation of the drone. And the close
Okay.
to goal is a signal that is true when the drone has reached the waypoint that was specified.
Okay.
So it effectively
Okay.
stops the drone.
Yep. That's fairly simple.
Yep. For simplicity, we'll just change the altitude to 5 meters so that the drone does not meet any obstacles for now.
Yep. Okay.
So the drone is going to 5 meters now. And we can see that it's moving towards the QR code.
So while it's doing this, can you actually view the laser scan data in real time, or the camera data in real time?
Yeah, you can see the laser scan data. So here we can see that it doesn't see any obstacles at this height.
Correct, because it's above
Yes.
everything. Huh.
And we can also see the position of the drone that is updated.
Oh, okay. So you can actually actually design optimized controllers for this, because you don't want, you can choose your paths and all that kind of stuff. That's
Mm.
cool.
So now the drone has reached the QR code, and we can observe that the
Mhm.
close to goal signal is true.
Ah, okay.
So
Okay.
I forgot to mention that we can visualize all the signals in real time in Simulink.
Okay. How do you do that?
You just need to click on the signal and it toggles the
Okay.
value. Otherwise, you can right
Huh.
click and select show value label of selected port.
Oh, okay. Okay.
It's quite
That's cool.
convenient, yes.
All right. So now that but I see. So this algorithm that you put in is basically just a simple path following algorithm. You just had the destination points, and the drone drove there. What happens if you have obstacles in the way? Can you add like an obstacle detection algorithm in there, or an obstacle avoidance algorithm
Sure,
as
let's
well?
add the obstacle avoidance algorithm now.
Okay. And again, it's just a simple copy paste into the main model. This is really cool.
Yes, it is. So the obstacle avoidance algorithm takes place within the path following and the output, and
Okay.
it what it actually does is that it modifies the trajectory given by the path following algorithm to avoid obstacles.
Okay. Huh.
Um, for it to,
And it's also taking in a laser scan as
yes,
well.
so we need to connect the laser scan data to it.
Okay.
We need to connect the target direction, and the
Uh-huh.
output are the linear and angular velocities.
Okay.
I'm going to restart Gazebo to set a new drone position. Um, so you remember that in the previous simulation we set the altitude reference to 5 meters, but now we'll change
Uh-huh.
this to 1 meter so that the drone actually meets obstacles.
Oh, okay.
So yeah, I'm just changing the altitude reference to 1 meter,
Okay.
and let's start the simulation.
Oh, nice. So it's actually seeing the wall now, and it's looking for a way to go through.
One of the settings is the radius of the drone. At the moment, it's a bit large, so that the drone chooses the largest
The
windows.
larger
Yeah.
window. But again, those are all tunable parameters, so users could chain that, depending on what they're trying to test.
Exactly.
Okay. And are these all PID controllers that you're using, or
Now, this the obstacle avoidance algorithm is a block from the is a block from the Robotics
oh,
System
okay.
Toolbox, and it's using vector field
Oh,
histogram.
so these are all canned algorithms,
Yes, exactly. It's ready to use from the Robotics System Toolbox.
and now it'll go and find the QR code. That's really cool. Yeah, it looks like it's found the QR code.
Of course, you all the data from that you receive in Simulink, you can log it and use it to replay the simulation afterwards or analyze it afterwards.
Oh, okay.
So you can compare
Okay.
different mission algorithms together.
Okay. Nice. Thank you for this demonstration, Julian.
You're welcome. So in this software demonstration, we saw how you could model an indoor environment in Gazebo and load a model of a drone and its sensors. Also, we saw how you could implement and quickly debug and tune algorithms in Simulink. Also, using the Robotics System Toolbox, you are able to use ready-to-use algorithms in Simulink. And also, you will be able to generate C code or ROS node from Simulink.
Cool. And yeah, so if you guys want to learn more about how to get started with MATLAB and Simulink and ROS, again, as I told you earlier, my colleague Sebastian Castro has been working on a few videos for that, and they're also a part of the MATLAB and Simulink robotics arena, and you can find those there. So finally, coming back to some resources for you guys. Again, if you like the video and you want to hear and you want us to create more videos on these topics, or any topics that interest you, please feel free to contact us via email at the roboticsarena@mathworks.com, or on our Facebook group. As I told you about the other robotics arena videos, you can find many more resources for um, to help you get started with student competitions in the robotics and unmanned systems domain by visiting the robotics arena webpage, and you can find that at mathworks.com/robotics arena. Don't forget our software offer. We offer complimentary software to student teams, um, which has products like the Robotics System Toolbox and the Aerospace Toolbox on there. Um, Please take advantage of this offer. Find out more about this software offering at the link on the screen. And finally, visit our blog. We've got a Racing Lounge blog, and yes, it does include robots. Thank you so much.